Hello, this is Dr. Armand again, bringing you another exciting lecture in the realm of General Chemistry 2. Today we'll be looking at applications of kinetics involving substitution reactions for organic reactions. I've already posted a video like this before, just going to post another one to kind of focus on, it's a shorter video, focus more on, we're going to be looking at SN2 reactions, very simple, fundamental SN2 reactions, nothing too complicated. And also explain how solvent plays a role in affecting the activation energy of substitution reactions, and finish up with a couple of practice problems. So sit back, relax, and enjoy the show. First, we're just going to warm up with a little basic mechanism here. And so we have this reaction mechanism, and we want to identify a few things. We want to know, are there any reaction intermediates? If yes, we need to identify them. Any catalysts used. And we want to write the energy diagram for this. These are the three things we want to do with this reaction mechanism. So first off, we want to see, are there any reaction intermediates in this mechanism? And again, reaction intermediates produced in one step, consumed in a following step. So we look at step one, we have hydrogen and palladium, give us this palladium hydrogen species. And then this palladium hydrogen species is used up in the second and third step. So PDH, shown here, is a reaction intermediate because it gets produced and then consumed. So PDH is a reaction intermediate. Now we go to step two. In step two, we take C2H4 reacted with PDH, we get this C2H5PD. Now, this C2H5PD is produced in step two, and then it gets consumed in step three. So since it gets consumed, produced and consumed, it's a reaction intermediate. So in this example, we have two reaction intermediates. And then we get our products. So there are two reaction intermediates in this reaction mechanism. Now we want to look at the catalyst. So the catalyst, again, consume in one step, produce in another step. So here you see we consume palladium, and in the last step we reproduce palladium. And so this is for this reaction mechanism is for the hydrogenation of ethene. And so you see the only things left after the reaction intermediates and the catalyst is just H2, C2H4, and C2H6. So that's what's going to be in the overall reaction. So the catalyst here, and this is a heterogeneous catalyst, it would be palladium. So now we need to draw the energy diagram for this. So let me erase all these marks. So we see here we have three steps. 1, 2, 3. That means we're going to have 3 humps. Now, we got to determine the slow step here, and for this to be a valid mechanism, there can be no reaction intermediates in the rate law, and well, there can't be no catalyst either. So technically, we don't know. But let's hypothesize here, and just for illustration purposes, let's say step 1 is the slow step. Well, no, not step 1, because it has the catalyst. we'll say step 2 is the slow step. And the reason we're saying step 2 is the slow step is because since step 1 is fast and reversible, we can actually substitute out the reaction intermediate from the rate law. But we'll just say for illustration purposes that step 2 is the slow step. So we have our reactants. We have step 1, step 2, step 3. And so now with the reactants again, H2 and palladium, the products, C2 plus palladium. So in the first step, we get a reaction intermediate. And then in the second step, we get another reaction intermediate. And so this is what the energy diagram of this mechanism could look like. Again, 3 steps, 3 activation energies. The slow step is the one with the highest energy. Here, just to kind of help us understand carbocations, say which of the following haloalkanes would form the most stable carbocation. And so the most stable carbocation comes from the most substituted haloalkanes. You want to see which one has the most sticks, as I like to say, carbon sticks, off of the carbon attached to the halogen. So here, let's identify the carbon attached to the halogen in each one of these. Now let's see how many carbon sticks are off of each of them. So this one A has 2 carbon sticks, so it's a secondary alkyl halide. B has 1 carbon stick, so it's a primary alkyl halide. C has 1 carbon stick, so it's a primary alkyl halide. E has 1 carbon stick, it's a primary alkyl halide. F has no carbon sticks, it's a methyl halide. And D has 3 carbon sticks, it's a tertiary alkyl halide. So since it's a tertiary alkyl halide, it's going to form the most stable carbocation. So D would be the correct answer. So in a previous lecture, we talked about SN1 reactions. Now we're going to look at SN2 reactions. And so with SN2 reactions, they're a little bit different than SN1 reactions. So SN means substitution of nucleophile, 2 means it's a bimolecular step. Excuse me, bimolecular or a bimolecular elementary step. And it's a 1-step mechanism. And in this 1 step, the nucleoside performs a backside attack to the leaving group. And the leaving group is the halide that leaves. And at the same time the halide leaves, the nucleophile attacks from the backside and reacts to form that carbon nucleophile bond. And so again, SN2 reactions attack, the nucleophile attacks from the back. For SN1, there's no reason for it to attack from the back, because in SN1, you form the carbocation first and then the nucleophile attacks. But with SN2, the nucleophile performs a backside attack to where the leaving group is leaving. And so as you can imagine, the more carbon groups you have attached to the carbon that is bound to the halide, the more difficult it's going to be for that nucleophile to attack. So in this second picture here, we see it says increasing steric hindrance. So increasing steric hindrance is increasing the bulkiness around that carbon attached to the halide. So as you increase this steric hindrance, you decrease the reactivity of an SN2 reaction. So a methyl halide would react the best for an SN2 reaction because there's very little steric hindrance on that carbon. Next would be a primary alkyl halide. So we'll call this a 0-degree alkyl halide. So no carbon groups attached to that carbon. First degree alkyl halide, second degree, and tertiary third degree. And so as you add more carbon groups, it gets more bulky, it decreases the reactivity of the SN2 reaction. So for SN2 reactions, tertiary alkyl halides generally do not undergo SN2 reactions. It's mainly methyl halides can do it, primary halides can do it, and even some secondary halides can undergo SN2 reaction. But tertiary alkyl halides generally do not undergo SN2 reactions. And again, these are one-step mechanisms, so there's only one energy barrier to overcome in the reaction mechanism. So if I was to draw the energy diagram of an SN2, it would look something like this. So that's the energy diagram of an SN2 reaction. Notice there's no reaction intermediate. There's only one activation energy to overcome. So what's occurring in the transition state of this SN2 reaction? Again, this is a concerted reaction. So the nucleophile attacks the backside of the carbon halide bond. So with the transition state, the carbon bromine bond starts to elongate, the carbon nucleophile bond starts to form. And then as it forms products, the carbon nucleophile completes, it forms a bond, and then the bromide leaves. And so that's what's occurring at the transition state. Nucleophile is coming in, bromine is going out, and then eventually when we get to the products, we form the we substitute the nucleophile for the bromine. So notice they're about 180 degrees apart, the nucleophile and bromide on both sides of the carbon. So like I said, it's a concerted biomolecular reaction. Again, concerted means it happens all in one step. So what happens is we have what is this? 2 bromo propane, and we reacted with lithium hydroxide. So hydroxide is our nucleophile. We use a solvent THF. We get the substituted isopropanol. Now what happens at the same time, the nucleophile attacks from the backside, the bromide leaves, and then we get our substituted product. And again, this is a one-step reaction. So as the reactants, we get to transition state, and then we roll down to get to the products. And if we're dealing with what's called Gibbs free energy, this reaction is spontaneous, means it's exergonic. So delta G is less than 0. Now what happens here at the transition state is we're breaking a carbon bromine bond, which is basically nonpolar, and we're forming a carbon-oxygen bond, which is polar. So this carbon sigma bromine bond is breaking, which is nonpolar, and we're forming a carbon oxygen sigma bond, which is polar. So therefore, since there's a greater polarity or greater dipole moment in the carbon oxygen bond, it makes it a more stable bond. That's why generally substitution reactions are exergonic reactions, because they form a more stable bond. In all substitution reactions, we're forming a more stable bond because we're going from something that has a very weak dipole moment, like a carbon halide bond, to something with a very large dipole moment, like a carbon oxygen bond. So again, this is the characteristics of a SN2 reaction energy diagram. Make sure you know the different characteristics. So here we have methyl bromide. So this will undergo SN2. We have our nucleophile, which is the acetate ion. So it's electron rich. And then we get our substituted product and bromide. So again, we start with the reactants. As we get up to the transition state, this carbon-oxygen bond starts to form, the carbon-bromine bond starts to break, and then we roll downhill to get to our products. Again, these are generally exothermic reactions. So this is just comparing methyl bromide with dimethyl bromide and showing you the difference in activation energies. Because again, with methyl bromide, it's a lower activation energy because it's easier to attack from the backside, not that much steric hindrance, aka not that many bulky groups. So the activation energy is low to reach the transition state for methyl bromide. Again, it's easier to do the backside nucleophilic attack. Now with the dimethyl bromide, now we have some bulkiness in that alkyl halide, so it's a little bit harder for the nucleophile to attack from the backside. So since it's a little bit harder, it has a higher activation energy, which leads to a slower reaction. So it will react, but it'll take a little bit longer because now it's a little bulky. It's harder for that nucleophile to squeeze in and attack from the backside, while the leaving group, aka the bromide, is leaving. So again, the less substituted alkyl halides, the easier it is for the backside nucleophilic attack, making lower activation energy and faster reaction. So if you have a methyl halide or a primary alkyl halide, they tend to undergo only SN2 reactions. Now if you have a secondary alkyl halide, typically SN2, but there can be some SN1, and for tertiary alkyl halides, only SN1 reactions. So notice methyl bromide lower activation energy than dimethyl bromide. And this is due to the increase in the bulkiness or steric hindrance of the alkyl halide. So we've talked about SN1 reactions. It's a two-step mechanism. We've talked about SN2 reactions. It's a one-step biomolecular mechanism. So now we're going to tell you just briefly how solvent affects these types of reactions. And so if you remember, for SN1 reactions, we form a carbocation. And in SN2 reactions, we don't. In both of these reactions, we're using a nucleophile. Again, a nucleophile is something like hydroxide or acetates or ammonia, methylamide, things like that, electron-rich species. And generally, when you have a nonpolar and polar solvent, when you have a polar solvent, it helps lower the activation energy of your reaction. And that's because nucleophiles are generally more soluble in polar solvents. Or more soluble, not more. Nonpolar solvents like hexane, benzene, heptane, pentane, those are nonpolar solvents. We're talking about alcohols, water, acetone, THF, etc., DMF. And so your nucleophiles tend to be more soluble in polar solvents compared to nonpolar solvents. Therefore, it makes it easier for the reaction to occur. So if you do your substitution reaction in a polar solvent, it helps lower the activation energy. Now with SN1 reactions, remember we form a carbocation as a reaction intermediate. So our reaction intermediate is a carbocation. And so for SN1 reactions, it prefers a polar protic solvent. So SN1 prefers a protic polar solvent. And that's because with protic polar solvents, the solvent forms an ion dipole interaction with the carbocation. So when you use a protic polar solvent, it stabilizes the carbocation so that then the nucleophile can attack in the second step. So with SN1 reactions, again, we prefer protic polar solvents. Now with SN2 reactions, we prefer aprotic polar solvents. And that's because with SN2 reactions, if we use a protic solvent, the solvent will interfere with the nucleophile and kind of inhibit it from attacking the alkyl halide. So again, with SN2, we prefer aprotic polar solvents because if we use a protic polar solvent, it may interfere with the nucleophile. And we don't want it to interfere with the nucleophile because, again, as in SN2 reactions, as the leaving group is leaving, the nucleophile is attacking. And now if you have a protic polar solvent, it's going to interfere with that. So we prefer an aprotic polar solvent. Now your question obviously is, what's the difference between protic and aprotic polar solvents? So polar solvents can be divided into two groups. Protic means it's involved in hydrogen bonding, has hydrogen bonding ability. And such examples are alcohols like methanol, ethanol, and water. These are probably the most common protic solvents because they can hydrogen bond because they have a hydrogen attached to an oxygen. Now, aprotic solvents are polar but do not have hydrogen bonding ability. And what this means is they don't have a hydrogen attached to an oxygen nitrogen atom. So common examples of aprotic solvents or aprotic polar solvents. We're looking at acetone. We're looking at DMF, dimethyl 4-amide. We're looking at DMSO, dimethyl sulfonoxide, and we're looking at THF, tetrahydrofuran. These are all types of aprotic polar solvents. Now to show you what these look like, Acetone looks like this. That's acetone. DMSO is very similar to acetone, except there's a sulfur instead of a carbon. That's DMSO. DMF, similar kind of. This is DMF. And then THF looks like this. 5-member ring with an oxygen at the apex of the roof. So again, this is acetone, DMSO, DMF, THF. And these are common solvents that you use in organic chemistry laboratory. So again, in summary, SN1 reactions prefer polar solvents over nonpolar solvents because better solubility of the nucleophile. So if you can, choose a polar solvent. Now with SN1 reactions, we prefer, or it prefers, a protic polar solvent, and those are polar solvents that have hydrogen bonding ability with themselves, so they can hydrogen bond with the cells because they have a hydrogen attached to an oxygen. And what happens is these protic polar solvents form an ion dipole interaction with the carbocation, stabilizing it so that the nucleophile can attack. Now with SN2 reactions, it prefers aprotic polar solvents, because if you have a protic solvent in an SN2 reaction, it's going to interfere with the nucleophile and kind of inhibit the nucleophile from attacking or backside attacking of the alkyl halide. So we prefer for SN2 aprotic polar solvents like acetone, DMF, DMSO, THF. Now let's look at some examples. So here we want to know, we're given a list of reactants that can undergo substitution reactions, and we want to know which of the following would easily observe the following energy diagram. So when we say easily observes, we mean which one's going to have the lowest activation energy for this energy diagram. And notice here that the energy diagram has two steps, or two activation energies, which means it has a two-step mechanism. Because there's two activation energies, there's two-step mechanism. So what this is going to be an SN1 reaction. Because again, the energy diagram shows two activation energies which correlate to two steps in the mechanism. Therefore, it has to be SN1 mechanism, or SN1 reaction. Now, the lowest activation for an SN1 reaction is the most substituted alkyl halide. So if we look through here, we're looking at alkyl halides, but hey, D, there's no halide on it. So D we can disregard. Now from A, B, C, and E, we need to choose the one that is the most substituted alkyl halide. And so if we look here at this carbon, or the carbon attached to the halide, we'll see which one has the most carbon sticks off of it. And so we see that the first one just has one group. The second one has two carbon sticks, two groups of carbon sticks. The third one has no groups of carbon sticks. And the fourth one has three groups of carbon sticks. So E would be the one that would observe the following energy diagram with the lowest activation energy. C would not exist because methyl bromide has a very highly unstable carbocation, so it would be very hard for the nucleophile to attack. So here we have another example. Which of the following substitution reactions would have the lowest activation energy using the following energy diagram? So we need to investigate this energy diagram. We see, hey, in this energy diagram, we just have one step because of one activation energy. So since it only has one step, this is an SN2 reaction. And since it's SN2, we want to look for the least substituted alkyl halide. So we circle the carbon attached to the halide, and we'll see how many carbon groups or carbon groups are off of it. So we're looking for the one with the least number of carbon groups attached to the carbon bound to the halide. So on the first one, we have 2 groups. Second one, we have 1 group. The third one, we have 1 group. Here we have 1 group. And on D, we have 3 groups. And on F, we have 0 groups. So F would be the combination out of all the ones shown here that would have the lowest activation energy for an SN2 reaction because it's the least substituted alkyl halide, so it's very easy for the nucleophile to attack from the backside. Now, out of all of these, D would not occur because D is a tertiary substituted alkyl halide, and since it's so bulky, it'll be very hard for a backside attack. So one last one, we want to know how solvents would help lower the activation energy for this reaction. So we have lots of different solvents. We want to know which of the following would help lower the activation energy of this reaction. And it gives us the energy diagram of this reaction. So what we need to do is when we need to look at the energy diagram. Okay, we see here that we have 1 step. So this is a 1 step, or excuse me, we have 1 activation energy which correlates to 1 step. So since this is 1 step, it's an SN2 reaction. And for SN2 reactions, what type of solvent do we prefer? That's right, aprotic polar solvents. So the ones that would help lower this activation energy are the solvents that are aprotic polar. Now we can go through and mark out the ones that are non-polar. So all we're looking for non-polar is carbon and hydrogens or just carbon sticks. So we see here that B only has carbon sticks, so it is non-polar. So that wouldn't help lower the activation energy. E only contains carbon and hydrogen, so this is also non-polar. Now that we've gotten rid of the non-polar ones, we need to determine from the polar ones which ones are aprotic and which ones are protic. Now the protic ones have the ability to hydrogen bond with themselves, such as water and alcohols. They have a hydrogen attached to an oxygen. So H2O is a protic polar solvent. We can get rid of that. Ethanol is a protic polar solvent. We can get rid of that one. And so what we have left are the ones that are aprotic. THF is an aprotic polar solvent, and DMSO is an aprotic polar solvent. And so these are the 2 solvents that you could use to help lower the activation energy of your SN2 reaction because they won't interfere with the nucleophile while it's attacking the alkyl halide. So again, this is THF, and this is DMSO. So just to kind of recap, a lot of things covered, just kind of summarize. SN1 reactions are a two-step reaction where the first step is a bimolecular step, and the first step is always the rate determining, excuse me, let me back that up. So for SN1 reactions, this is two-step mechanism. The first step is always the formation of your carbocation, and the first step is always the rate determining step. And the carbocation is always the reaction intermediate in an SN1 reaction. Now with solvents, SN1 reactions prefer polar over nonpolar solvents. Secondly, SN1 reactions prefer the best is protic polar solvents because they can stabilize the carbocation by forming ion dipole interaction with the carbocation. So an SN1 reaction will have two activation energies in the energy diagram. For now for SN1 reactions, it prefers the more substituted alkyl halides like secondary and tertiary alkyl halides, because tertiary alkyl halides, for example, have very stable carbocations. Now for SN2 reactions, here it's a one-step bimolecular mechanism where everything happens at once. It's called a concerted reaction. And so for SN2 reactions, you only see one activation energy. Also, SN2 reactions prefer polar solvents, but to be very specific, it prefers the best is aprotic polar solvents. These cannot hydrogen bond with themselves. So these are things like DMSO, THF, DMF, and acetone, for example. Now, SN2 reactions prefer those alkyl halides that are not extremely substituted, like methyl halides, primary alkyl halides, even maybe secondary alkyl halides. But methyl and primary most definitely will undergo SN2 reactions because it's not very bulky. It's easy for the backside nucleophilic attack. So that's kind of the conclusion of substitution reactions and how, based on the reactants and the reactant conditions, we can get the mechanism and the energy diagram from it. Now, pretty much all substitution reactions are exothermic because you're going from something, a carbon halide bond, which doesn't have a very large dipole moment, even nonpolar, to go into a carbon-oxygen bond, which is a very large dipole moment compared to its former. Therefore, it's going to be more stable, lower in energy. So I hope you enjoyed this expedition into kinetics of substitution reactions, and maybe it'll be beneficial if you end up taking organic chemistry. Again, this is just an introduction, very specific types of compounds we're looking at, just to kind of give you an idea of how this stuff works. So on that note, I hope you enjoyed the show, and Dr. Armand signing off. Until next time.